Imagine you have this beautiful, pristine classic car, like a really nice vintage 1970s chassis.
Okay, I am picturing it.
Right. And now you want to take this classic car and race it in a modern hypercar rally. So you take this massive, insanely powerful, screaming, modern water-cooled engine, and you just drop it right into that vintage frame.
Yeah, I mean, the torque alone on that it would snap the chassis in half before you even got out of first gear.
Exactly.
The suspension would completely collapse, the old exhaust couldn't handle the output, and, those legacy air intakes would basically starve the engine while it melted the surrounding bodywork.
It would be a complete disaster. And that is exactly the paradox we are looking at today in the world of high-performance computing.
It really is the perfect analogy for what is happening in data centers right now.
Because we always talk about the software side of artificial intelligence, right? The massive neural networks, the trillions of parameters, the seemingly magical way a large language model can generate code or, like, art and sound.
Right, the stuff that makes the headlines.
Exactly. But every single time you type a prompt into one of those tools on your phone, you are forcing a physical piece of silicon somewhere in the world to work incredibly hard. Because the cloud is a physical place, like it's a building.
It is very much a physical place. Typically, a vast, sprawling warehouse just filled with thousands of metal racks.
Right.
And right now, the tech sector is hitting this massive physical bottleneck because the compute power of AI is scaling exponentially, requiring just unprecedented amounts of electricity.
And generating unprecedented amounts of heat, presumably.
Oh, absolutely. But the physical infrastructure of the buildings housing that compute, specifically the power delivery and the cooling architecture, is fundamentally stuck in a previous era.
Which brings us to our source material for today's deep dive. We are looking at a stack of highly technical documents today.
Very technical.
Yeah, specifically a detailed technical data sheet and a series of schematic engineering images for this piece of hardware designed by Supermicro. It is called the Liquid-to-Air Sidecar CDU, which stands for Cooling Distribution Unit.
And this isn't just, some generic piece of hardware. It represents a highly engineered bridge technology.
Right, so our mission today is to decode exactly how this giant metal box acts as that bridge. We are going to figure out how this machine takes the legacy infrastructure of the past 20 years and somehow allows it to support the ultra-dense, ultra-hot future of AI computing.
All without forcing operators to tear down their existing buildings, which is the really crucial part.
Exactly. So, okay, let's unpack this.
Well, the best way to approach this data sheet is to realize that while it is packed with kilowatt ratings and API protocols and redundant pump specs, it's fundamentally a story about thermodynamics.
Thermodynamics. Okay, so we are going back to physics class.
Just a little bit. It's about adapting to the sheer, uncompromising physical limits of heat, power, and architectural legacy. So, to go back to your classic car analogy, the engine here is the modern AI server rack.
Right.
Historically, server racks were like standard sedan engines. I mean, they definitely generated heat, but you could manage it simply by blowing cold air across them.
Like just aiming a fan at it, basically.
Pretty much. You had small fans inside the server chassis itself, and then massive air conditioning units pumping cold air into the room.
Right, the classic air-cooled data center. I mean, anyone who has ever stepped inside one knows exactly that feeling.
Oh, yeah.
It's deafeningly loud because of thousands of tiny fans just screaming at 10,000 RPM, and you practically need a winter coat because the room's AC is blasting at full capacity.
Yeah, that was the standard for 20 years. But today's AI racks, which are densely packed with the latest generation of GPUs, are generating thermal energy at a scale that ambient air simply cannot absorb or move quickly enough.
Because air isn't actually that great at holding heat, right?
Exactly. The specific heat capacity of air, its physical ability to hold thermal energy, is incredibly low. The industry has basically reached the physical limit of air cooling.
Wow.
To keep these new chips from physically melting their own silicon, the industry has to transition to liquid cooling. Because liquid, whether it's highly treated water or, specialized dielectric coolants, has a volumetric heat capacity thousands of times greater than air.
Thousands of times.
Yes. It is exponentially more efficient at grabbing heat directly from the chip and moving it away.
Okay, so if liquid is the future, that brings us to the core problem this Supermicro document claims to solve. Because the datasheet highlights a, quote, seamless rapid deployment for a seamless liquid-to-air cooling solution for air-cooled data centers.
That is a mouthful, but every word there is deliberate.
It explicitly states that this sidecar allows facilities to adopt liquid cooling for high-density AI and HPC, which is high-performance computing racks, without needing water cooling towers or primary facility water loops.
And that specific phrase is the entire crux of the engineering challenge here. Without the need for water cooling towers or primary facility water loops.
Now, I have to stop here, because looking at the physics of this, I need to make sure we are painting a clear picture for you, the listener. The document insists this is a liquid-to-air deployment.
Right.
It rejects the heat from the rack directly into the ambient air of the room. But, I mean, if this is a liquid cooling system, why on earth is it dumping the heat back into the air?
It sounds completely counterintuitive, doesn't it?
It totally does. I thought the whole point of moving to liquid was because air was no longer sufficient. If I'm plumbing water to my ultra-hot processors, shouldn't that water carry the heat all the way out of the building to a cooling tower?
That would be the logical assumption, yes.
Dumping it back into the room just feels like an oxymoron. It's like using a bucket to bail water out of a sinking boat, but just pouring it onto the other side of the boat.
That is a great way to look at it. And you are right. If you were building a brand new multi-billion-dollar data center today, explicitly designed from the ground up for AI, you would do exactly what you said.
Right.
You would build immense water cooling towers on the roof. You would run massive primary facility water loops, giant, heavily insulated steel pipes throughout the entire structure.
It's plumbing everywhere.
Everywhere. Under the raised floors, directly into every single row of servers. The liquid would enter the server rack cold, absorb the massive heat from the GPUs, and then that boiling hot liquid would travel all the way outside the building to release the thermal energy into the atmosphere.
Okay, so that would be the purpose-built hypercar chassis we talked about earlier,
Yeah.
designed specifically for that massive engine.
Precisely. But here is the stark reality of the global infrastructure landscape today. The vast majority of data centers operating right now were built 10, 15, or even 20 years ago.
Long before AI was doing what it does now.
Exactly. They were designed entirely around air. They possess zero facility-wide liquid plumbing. Their entire thermal management strategy relies on giant industrial air conditioners.
Like those CRC units, right?
Yes, CRC units, computer room air conditioning, basically just massive ACs pushing chilled air under a raised floor.
So if you're a major enterprise and you just spent, I don't know, $20 million acquiring a fleet of the newest AI servers, and you wheel those racks into your existing 10-year-old data center, you're trapped.
You are completely trapped. You literally cannot plug them in.
Wait, really? You just can't even turn them on?
If you boot them up, they will generate so much concentrated heat that they will overwhelm the ambient air conditioning in that specific aisle almost instantly.
Wow.
The ambient air temperature around the rack will just skyrocket, the servers will hit their thermal limits, and they will automatically trigger an emergency shutdown to prevent the silicon from catching fire.
That is terrifying. And I'm assuming retrofitting a whole building isn't just like a weekend project. You can't just call a commercial plumber to install a massive facility water loop while the rest of the data center is live.
No, it is practically impossible without catastrophic disruption.
Because you'd have to tear everything up.
Exactly. To retrofit a legacy data center with primary facility water loops, you would have to shut down entire sections of the building. You would have to bring in heavy machinery, welders, pipe fitters.
Just a total construction zone?
You'd be drilling through concrete floors and laying massive pipes directly over or under live IT equipment that is currently running, critical banking infrastructure or healthcare databases or global cloud services.
Oh man, the liability alone.
Right. The risk of a leak, a dust cascade from the drilling, or an accidental power cut is astronomical. The downtime alone would cost tens of millions of dollars before you even paid for a single piece of pipe.
Which perfectly positions why this Supermicro L2SideCar exists. Because looking at the text here, it says it leverages existing air-cooled infrastructure and completely eliminates the need for new facility-wide modifications.
It's essentially a localized rack-level translation device for heat.
A translation device for heat. I like that.
Yeah, it operates on a principle of thermal triage, basically. You get the targeted high-efficiency benefits of liquid cooling exactly where you need it, most directly touching the incredibly hot AI processors.
But you don't have to change the building.
Exactly. You interface with the building using the medium the building already understands, which is air.
Okay, let me trace the physics based on what the datasheet outlines here, and you tell me if I have this right.
Go for it.
So inside the high-density AI rack, You have liquid flowing through microchannel cold plates that are physically mounted directly on top of the CPUs and GPUs. That liquid absorbs the intense concentrated heat. But instead of that liquid traveling all the way out of the building to a roof tower, it only travels about 2 feet to the left or right, straight into this adjacent sidecar cabinet.
Right.
Once that extremely hot liquid enters the sidecar, it runs through a massive heat exchanger, and the sidecar uses its own incredibly powerful internal fans to blast the ambient air of the data center across that exchanger, ripping the heat out of the liquid and throwing it into the room.
You have captured the exact thermodynamic cycle there. It's brilliant in its simplicity.
So it just offloads it to the room.
Yes. By forcing that concentrated heat to spread out into the ambient air of the room, the sidecar allows the building's existing legacy CRIC units to deal with it.
Ah, I see.
Because the building's old air conditioners have no idea that the heat originated from a liquid-cooled GPU array. Their sensors just detect that the ambient room temperature is rising, and they kick on to cool the room down exactly as they were designed to do 20 years ago.
It's a structural hack. It allows a facility manager to achieve the holy grail here, which is localized modernization with zero facility downtime.
That is the big selling point.
Because you wheel this sidecar in next to your new AI rack, you fill the localized loop with coolant, plug it in, turn it on, and boom. You have instantly modernized a 10-square-foot footprint of your facility without touching the infrastructure of the surrounding 100,000 square feet.
Exactly. It isolates the thermal modernization purely to the IT deployment layer, entirely bypassing the facilities layer. It's a massive headache saver.
Okay, so we understand the overarching purpose. It's the ultimate legacy retrofit tool. But since our listener can't physically see the schematic images and photographs we have in front of us, we really need to spend some time exploring what this hardware actually looks like.
We definitely should.
Because looking at these diagrams, I am genuinely taken aback by the sheer, unapologetic industrial scale of this thing.
It is certainly not a sleek consumer-grade aesthetic, that's for sure. Form strictly follows function here.
Yeah, because when you picture a typical server, you usually envision something quite slim, maybe a brushed metal chassis, an inch or two thick, that slides neatly into a standard 19-inch rack.
Very clean, very modular.
Even a fully populated server rack is just a neat, monolithic rectangular tower. But this L2A sidecar, I mean, it looks like a miniaturized chemical plant.
It really does. The visual evidence in the source material provides a masterclass in heavy-duty mechanical engineering.
So let's start with the exterior. It's a colossal, matte black, heavy-duty metal cabinet. We'll get to the exact dimensions later in the specs, but visually, it just dominates the space.
It's imposing.
Very. And the front doors aren't solid metal. They are composed of reinforced mesh and glass panels. And peering behind those panels, you don't see circuit boards or, like, blinking Ethernet lights. You see an absolute labyrinth of heavy plumbing.
Right, and that plumbing is the vascular system of the entire operation. It is worth noting the distinct difference in the materials used here compared to what some people might be familiar with in high-end consumer electronics.
Yeah, that's exactly what I was thinking. Because when you see a PC gamer build a custom water-cooled rig on YouTube, they use these pristine, clear, flexible acrylic or silicone tubes.
Usually filled with neon pink or bright blue UV reactive fluid.
Exactly. It looks like a prop from a sci-fi movie. It's very flashy. But this Supermicro unit is the exact opposite. This looks like the plumbing you would see in a municipal water treatment facility or like the engine room of a nuclear submarine.
You are looking at rigid, thick-walled, industrial-grade metal piping, stainless steel, and heavily reinforced polymers. There are massive flange joints, industrial ball valves, analog pressure gauges, and heavy-duty locking mechanisms.
And if you follow that maze of silver piping down to the base of the unit in this primary schematic, you find the heart of this system. Sitting at the very bottom are these two incredibly robust, heavy-duty blue circular pumps.
They look serious.
They look like they weigh 100 pounds each.
Those are industrial centrifugal pumps. They are designed to maintain constant, high-pressure, volumetric flow against significant internal resistance. And directly behind that labyrinth of pipes, taking up what looks like the entire rear half of the cabinet's internal volume, are dense, towering banks of copper-colored material.
Basically floor-to-ceiling radiators. It looks like a solid wall of copper fins.
Yes. And that visual heft, the industrial pipes, the massive centrifugal pumps, the sheer volume of copper is necessary because of a very specific metric listed in the text. Cooling capacity. Up to 500 kilowatts.
500 kilowatts.
We really need to pause and quantify what 500 kilowatts of thermal energy actually represents in a physical space, because it's hard to grasp.
Yeah, 500 kilowatts is a totally abstract number to most people. How do we contextualize that amount of raw heat?
Let's break it down to something familiar.
Hmm.
Think about a standard plug-in electrical space heater you might use in your living room during the winter.
Okay, sure.
A typical space heater draws about 1,500 watts, or 1.5 kilowatts. When it's running on high, the metal grill gets hot enough to burn your skin, and it can comfortably heat a small room.
Right, they put out a lot of heat.
Now, to equal the heat output of one of these high-density AI racks, you would need to take over 330 of those space heaters, turn every single one of them up to maximum blast, and pack them all into a space roughly the size of a standard telephone booth.
Oh my God. That is horrifying.
It is extreme.
If you did that, the telephone booth would instantly turn into an industrial oven. The plastic would melt, the glass would shatter, and the entire thing would just catch fire in seconds.
Exactly. That is the sheer volume of thermal energy an AI rack generates. 500,000 watts of raw, unrelenting heat. Managing that kind of thermal density isn't really an IT problem anymore. It's a heavy industry problem.
Wow.
Air cooling a 500 kilowatt rack is physically impossible because air cannot absorb heat fast enough. You must use liquid to strip the heat away from the silicon, and once that liquid absorbs the heat, you must transfer it out.
Which explains the copper.
That is exactly why the Sidecar used such an immense volume of copper. Copper has one of the highest thermal conductivities of any common metal.
Okay, so the boiling hot liquid from the servers is forced by those massive blue pumps through the pipes and into these towering copper heat exchangers. The heat effortlessly passes from the liquid into the copper fins, spreading out over hundreds of square feet of surface area.
And then the airflow must be introduced.
Right, because I'm looking at another image here that shows the rear exhaust side of one of these configurations, and it is literally a wall of fans.
It's intense.
It looks like an array of incredibly deep, high static pressure fans stacked top to bottom, glowing with this aggressive green lighting, which I assume is Supermicro's corporate branding.
I would assume so. And those fans are not there for gentle ventilation. They are designed to generate immense static pressure, forcing thousands of cubic feet of ambient air per minute through the microscopic gaps between those dense copper fins.
It's just blasting the air through.
Violently stripping the 500 kilowatts of heat out of the copper and blasting it into the data center aisle.
The exterior of the cabinet also features some really telling details about how this is operated. Because I see an emergency shutoff button prominently displayed on the front frame.
Yes, the emo button.
It's one of those large physical yellow and red twist to release buttons, clearly labeled emo emergency machine off. And right next to it, integrated flush into the heavy metal door, is a digital touchscreen interface displaying a system dashboard.
We will certainly dissect the software and that touchscreen later, because the intelligence managing this fluid dynamics problem is just as critical as the hardware itself.
Oh, for sure.
But it's also worth noting the other environmental images provided in the source material.
Yes, there's a rendering showing a modular configuration where a line of these black L2A cabinets are interspersed seamlessly right next to standard IT server racks, demonstrating how they integrate side by side on a typical raised data center floor.
Right, but more importantly, there's an image of a massive outdoor installation. It looks like a huge shipping container topped with a massive V-shaped array of giant industrial fans.
Yeah, I saw that.
The document categorizes this under their broader infrastructure solutions as a dry cooler water cooling tower.
Wait, but why include the outdoor giant if the whole point is the indoor sidecar? Like, isn't that contradictory to the pitch?
It acts as a visual anchor for the value proposition. That massive outdoor shipping container, complete with roof access, structural supports, and primary facility plumbing, is the infrastructure you would be forced to build if you couldn't use the L2A sidecar.
Oh, I see.
By placing that image in the documentation, Supermicro is basically presenting a stark choice. If your facility lacks the real estate, the capital expenditure budget, or the logistical ability to construct a 3-story outdoor cooling plant and pipe it into your building, simply roll this black cabinet next to your servers instead.
Man, it's an incredibly effective juxtaposition. You're effectively shrinking the footprint of a localized cooling tower down to a single sidecar. However, tracing those thick industrial liquid pipes inside the cabinet brings us to an inescapable anxiety. mixing hundreds of gallons of flowing liquid with millions of dollars of highly sensitive electronics.
It touches on the deepest, most ingrained paranoia of any seasoned IT professional.
I mean, historically, water and electricity are treated like mortal enemies in a data center.
Absolutely.
You spend your entire career making sure the building has a leak-proof roof, dual-layered waterproof membranes, and raised floors with water sensors explicitly to keep moisture away from the servers. And now, the engineers are telling you to wheel a pressurized water main directly into the server aisle.
It feels wrong on a primal level.
It really does, but the source material addresses this phobia immediately. The document explicitly details what it calls a closed-loop design for high reliability.
We need to unpack exactly what closed loop means in this specific thermodynamic context and why the document stresses that the loop is, quote, fully contained within the rack, completely isolated from the facility's primary water system.
I was trying to think of a good analogy for this. Initially, I thought about a hazmat suit, a perfectly sealed ecosystem protecting the delicate IT equipment.
Okay.
But a hazmat suit stops everything from crossing the barrier. It stops air, liquid, and heat.
Yeah.
That doesn't work here because the entire point of the sidecar is to let the heat escape.
Right, the heat has to move.
So a much better analogy would be a glass window in the middle of winter. The physical glass stops the freezing wind and the snow from getting into your living room. That's the water being contained. But the glass perfectly allows the thermal radiation, like the heat from the sunlight, to pass right through into the room.
That is an excellent way to visualize a heat exchanger. The physical fluid boundary is absolute, but the thermal boundary is entirely permeable.
Exactly.
Now, if we connect this to the broader realities of facility management, we have to look at the immense risks associated with relying on a building's primary water supply.
Right, because if you're tapping into the building's water, you are essentially outsourcing the safety of your multi-million-dollar AI cluster to whatever plumbing was installed in the building 20 years ago.
Exactly. Let's look at the mechanical risks first. What if a major pipe bursts 3 floors down in the office area of the building?
Someone flushes a toilet wrong or something.
Or a main line just gives out. The overall water pressure in the facility plummets. If your cooling sidecar relies on that facility pressure to push water over the GPUs, the flow stops.
Oh, wow.
Within seconds, your AI cluster overheats and the hardware fries. But the chemical risks are even more insidious than the mechanical ones.
The chemistry of the water itself. You mean like tap water versus purified?
Yes. Facility water loops are often treated for scale and rust, but they are not pristine. They can contain microscopic particulate matter, dissolved minerals, rust from degrading iron pipes, or even biological growth like algae if the treatment fails.
Wait, algae in a server. And if that water gets into the server, what happens?
Well, the microchannel cold plates that sit directly on top of the AI chips have microscopic fins designed to maximize surface area. They are thinner than a human hair.
Okay.
If a tiny piece of rust or a fleck of scale from the building's old pipes enters that cold plate, it acts like a microscopic dam. It blocks the flow of coolant over a specific section of the chip.
Oh, I see where this is going.
That section instantly becomes a thermal hotspot and the processor burns itself out. Furthermore, if you mix different metals like the copper in the sidecar and the steel in the building's pipes with impure water acting as an electrolyte, you induce galvanic corrosion.
Galvanic corrosion.
The metals will literally eat each other from the inside out.
Oh, wow. So you absolutely cannot just hook a garden hose from the building's tap to your AI server.
Yeah.
You need incredibly pristine, perfectly balanced, chemically inert fluid.
Precisely. By designing this as a strict closed-loop system, fully contained within the sidecar and the adjacent IT equipment, Supermicro eliminates every single one of those external variables.
That makes total sense.
The coolant inside that loop is not building water. It is a highly specialized, chemically balanced, filtered fluid, often treated with specific anti-corrosives and biocides. It is managed solely by the sidecar. It never, ever touches the building's infrastructure.
The text states, this ensures reliable, maintenance-friendly operation for high-density AI and HPC deployments. It essentially creates a hard boundary of responsibility.
That is the operational genius of it. In a legacy data center, IT manages the servers and facilities manages the power and cooling.
It's 2 different departments.
Exactly. When they overlap, finger pointing inevitably occurs when something breaks. IT blames facilities, facilities blames IT. The closed-loop sidecar puts the control entirely in the hands of the IT deployment.
Because it's their box.
Right. If the fluid needs replacing, the IT team does it at the rack level. They don't have to submit a work order to the building's landlord to flush a massive facility pipe. The IT systems and the facility's air conditioning interact purely through the invisible exchange of heat into the ambient air, never through the physical exchange of fluids.
Okay, so the fluid is secure. The closed-loop design ensures it's isolated, chemically pure, and insulated from facility pressure drops. But having solved the plumbing vulnerability, we have to look at the next logical point of failure, the mechanical components themselves.
Yes.
Because what happens if this massive cooling system just breaks? Because the AI servers aren't going to politely pause their computation if a pump seizes up.
They absolutely will not. In the realm of high-performance computing, paranoia is basically an engineering prerequisite. The document outlines intense fail-safes under a section dedicated to maximized uptime.
It highlights two very specific redundancies. First, it states the system utilizes N+1 redundant pumps with automatic transfer switch, ATS. Second, it guarantees uninterrupted power continuity via redundant power supply units, PSUs. Let's break these down because while anyone in IT knows that redundancy is critical, implementing it with flowing liquid is vastly more complex than just, plugging in a backup hard drive.
To appreciate the necessity of these redundancies, we really have to revisit the brutal thermal dynamics we discussed earlier. If a cooling pump fails and the liquid stops moving across a 500 kilowatt AI rack, the temperature doesn't gradually rise over a few hours like a laptop sitting on a blanket.
Right, because there's practically no thermal mass to absorb the heat other than the silicon itself.
Exactly. If the flow of coolant stops, the localized temperature spikes instantly. The processors will undergo thermal runaway. We are talking about critical failure in a matter of seconds.
Seconds.
Yes, the system will forcibly sever power to itself to prevent the chips from liquefying, which instantly destroys whatever compute job was running. If you are training a massive language model, that job might have been running continuously for 3 weeks, costing hundreds of thousands of dollars in electricity and compute time.
All gone.
A 3-second interruption in coolant flow flushes all of that down the drain.
So failure is simply not an option. A single point of failure is an unacceptable financial risk. Which brings us to the N+1 pumps. Now, in standard IT parlance, N is the baseline number of components required to carry the load, and +1 means you have a spare.
Correct. So if the fluid dynamics at the 500 kilowatt rack require 2 massive pumps to maintain the necessary volumetric flow rate and pressure, the sidecar will be built with 3 fully plumbed pumps. That is the N+1.
But implementing N+1 with water is physically tricky, right? You can't just have a dry pump sitting on a shelf waiting to be used.
Exactly. It's not a cold spare. The +1 pump is fully plumbed into the manifold, submerged in the fluid, and sitting behind check valves to prevent backflow. It is a hot spare.
Oh, I see.
But simply having the extra pump installed isn't enough. If pump A physically fails, and a human technician has to recognize the alarm, walk down the aisle, manually turn a valve, and flip a switch to turn on pump C.
The servers are already dead.
Exactly. The silicon would be cooked before the technician even stood up from their desk. This is where the ATS comes in, the automatic transfer switch.
Yes. Let's talk about the ATS, just to clarify the mechanics here, because it's easy to visualize this incorrectly. The ATS isn't physically moving pipes or mechanically swapping a pump into place, right?
Correct. The plumbing is completely static. All pumps are already connected to the fluid loop. The ATS manages the flow of electricity.
Okay.
If it detects an anomaly, say, pump A's motor starts drawing excessive current because the bearing is seizing, or if it loses power entirely, the ATS instantaneously cuts the electrical current to pump A and routes it directly to the backup pump.
It's an electrical routing change that happens at the speed of light.
It happens in milliseconds. The backup pump spins up so fast that the overall hydraulic pressure in the cooling loop barely registers a dip. The AI servers and the incredibly expensive training models running on them are completely oblivious to the fact that a primary pump just died.
That level of fault tolerance is incredible. And this philosophy of complete paranoia extends to the electrical power delivery as well, right? Because what if the pump is perfectly healthy, but the specific electrical circuit providing power to the sidecar trips a breaker?
That is exactly why the text emphasizes redundant power supply units, or PSUs. In a modern mission-critical data center, power is delivered in an A-side and B-side configuration.
2 grids.
Yes. These are 2 completely independent electrical grids. They trace back to different uninterruptible power supplies, different backup generators, and sometimes even entirely different municipal utility substations.
So the sidecar has multiple power supplies, and you plug half of them into the A-side grid and half into the B-side grid.
Precisely. If a backhoe digs up a primary electrical main outside the building and the A-side grid goes dark, the sidecar's redundant PSUs seamlessly pull the required wattage from the B-side grid. The document notes this maintains cooling during critical operations and power disruptions.
Which really underscores a fundamental evolution in how we view data center architecture. The cooling is no longer just a secondary facility support system.
It is entirely symbiotic. The cooling infrastructure must be designed with the exact same level of fault tolerance, redundancy, and continuous power delivery as the AI servers themselves. If the mechanical cooling dies, the logical compute dies simultaneously. They are one organism.
Okay, so we've established the system is tremendously powerful, capable of moving 500 kilowatts of heat. And we've established it's highly resilient, utilizing closed fluid loops, hot spare N+1 pumps, millisecond ATS routing, and dual-corded power supplies.
Right.
But sheer power, especially mechanical power on this scale, is staggeringly expensive to operate. Running massive centrifugal pumps and a wall of high static pressure fans at maximum speed 24/7 would draw a massive amount of electricity.
It would be economically ruinous and incredibly wasteful, which transitions us into how this system manages its own parasitic power consumption. It's not just brute force, it requires significant intelligence.
The document highlights this under high energy efficiency with VFD optimization. It states the unit is integrated with variable frequency drives, or VFDs. The text explains that it, quote, can adjust fan speed intelligently based on real-time thermal demand, which reduces power consumption while maintaining optimal performance.
Yes, VFDs are a game changer.
Now, a fan adjusting its speed based on temperature isn't a novel concept on the surface. My laptop's internal fan spins up aggressively when I'm rendering video and goes dead silent when I'm just reading an article.
The conceptual goal is identical, yes, but the mechanism and the physics at this industrial scale are vastly different. In the past, legacy data center cooling fans were often simple alternating current induction motors running on a binary system.
On or off.
They were either powered on, spinning at 100% of their rated speed, or they were completely off.
So even if the server rack was idling or only generating 50 kilowatts of heat, the cooling fans were still screaming at full blast, consuming maximum electricity.
Exactly, and because of the affinity laws of fluid dynamics, that is incredibly wasteful.
Okay, I'm going to need you to unpack the affinity laws of fluid dynamics, because that sounds complicated.
It's a fascinating physical principle. In systems dealing with pumps and fans, the power required to run the motor is proportional to the cube of the rotational speed.
The cube?
Yes. This means if you can reduce the fan speed by just 20%, you don't just save 20% of the energy, you cut the power consumption by nearly 50%.
Oh, wow. So small reductions in speed yield massive exponential reductions in electrical cost.
Yes. And a variable frequency drive is the precise piece of electrical engineering that makes this possible for industrial motors. Rather than just giving the motor raw, fixed AC power from the wall, the VFD sits in the middle.
Like a gatekeeper.
Sort of. It takes the incoming electrical current and uses a process called pulse width modulation to precisely alter the electrical frequency, the hertz being delivered to the motor.
So instead of just on or off, the VFD can feed the motor a frequency that makes it run at exactly 41% speed or 78% speed, perfectly matching the required airflow to the exact thermal load at any given millisecond.
Exactly. The text accurately states this adaptive feature enables greener, cost-saving operation across AI and HPC clusters.
That makes total sense.
If your AI cluster finishes a massive multi-day training run at 3 a.m. and shifts into an idle state, the sidecar recognizes the drop in thermal output and instantly dials down the frequency to the pumps and fans. It saves massive amounts of electricity without requiring a human to flip a switch.
But the VFD is just the muscle, right? It's the actuator. The VFD doesn't inherently know when to slow down. The real intelligence is how the system knows exactly what speed to request. This is where the software protocols listed in the text come in.
Yes, the centralized management and monitoring integration is what elevates this from a mechanical appliance to a smart node on the network.
Let's look at the protocols listed. The text mentions the built-in touchscreen, which provides local control, a web UI for remote access, and support for something called Super Cloud Composer, which appears to be Supermicro's proprietary management dashboard. But then it lists these three industry standard protocols: SNMP, Redfish, and RESTful APIs. It says it uses these to monitor real-time temperature, pressure, flow rate, and pump status. So why do these specific software acronyms matter to a facility operating this hardware?
Because they represent a fundamental paradigm shift in data center operations. For decades, there was a strict firewall between the facility's equipment and the IT equipment.
Like we were talking about earlier with the different departments.
Exactly. The cooling system was a dumb mechanical beast managed by facility engineers reading analog pressure gauges and wall thermostats.
Right, the thermostat says the room is 75 degrees, so turn on the chiller. It's completely reactive.
Exactly. But by incorporating Redfish and RESTful APIs into the Sidecar's control board, Supermicro is bridging that gap.
Okay, I want to make sure I understand the mechanics of these protocols. An API, an application programming interface, is essentially a structured way for two distinct pieces of software, or software and hardware, to talk to each other over a network. But what is Redfish specifically?
Redfish is a highly secure, modern, industry-standard API designed specifically for managing server hardware. It uses human-readable JSON payloads delivered over standard web protocols.
Okay, so it's a language for servers.
Right. Historically, IT administrators used Redfish to query the health of their servers. They would send an API request to a server to ask, "What is the current temperature of CPU 0?" Or, "Are all your hard drives healthy?"
So it's an IT tool used exclusively to manage IT gear.
It was, but now this mechanical cooling sidecar speaks fluent Redfish. It has an API endpoint on the network. This means the IT department's automated orchestration software, the software that schedules and runs the AI workloads, can talk directly to the cooling pumps using the exact same language it uses to talk to the servers.
That is a massive operational leap. The cooling is no longer an isolated mechanical silo.
It becomes an integrated part of the logical network. Consider the operational advantage. An orchestration platform is about to launch an incredibly dense, highly parallel AI training workload. It knows that in exactly 30 seconds, the GPU utilization is going to spike from 10% to 100%.
And normally, the cooling system wouldn't react until the GPUs actually got hot, heated the liquid traveled to the sidecar, heated the copper, and the sidecar's internal thermostat finally registered the temperature spike.
Yeah.
That lag time is dangerous.
Exactly. But with the RESTful API integration, the IT orchestration software can send a programmatic payload directly to the sidecar's controller before the workload even starts. It can say, "A massive thermal spike is imminent. Spin the VFDs up to 90% capacity right now."
Wow. It shifts the entire thermal management strategy from reactive cooling to predictive cooling.
It is a beautiful symphony of mechanical engineering and software orchestration. The unit constantly monitors temperature, hydraulic pressure, and volumetric flow rate, feeding telemetry data back into the SuperCloud Composer dashboard, allowing for hyper-granular, real-time adjustments.
It's so smart.
It proves that achieving sustainability and efficiency in the AI era requires immense programmatic intelligence, not just bigger motors.
And for the technicians actually walking the physical data center floor, they have that built-in touchscreen on the front door. If a pump sounds irregular, they don't have to trace a network cable and log into a remote terminal. They just tap the screen on the cabinet to access real-time diagnostics.
It provides immediate, localized situational awareness, perfectly complementing the remote API capabilities.
We have spent a lot of time on the theory, the physics, and the software orchestration. But to truly grasp the scale of the engineering we are discussing, we have to look at the hard physical numbers provided at the end of the datasheet.
Grounding this in the physical specifications is crucial because it reveals the logistical reality of deploying this hardware.
The document details two specific models of the L2A sidecar. Let's start with the smaller of the two titans, the model LCS SCDU 200AR001. This is the unit designed for 200 kilowatts of cooling capacity. The maximum power consumption is 19 kilowatts.
Note that 19 kilowatts is just the parasitic power draw.
Meaning what?
That is the electricity required solely to run the pumps and fans inside the sidecar, completely separate from the power required by the AI servers.
Right. And the dimensions are substantial. It's 1,100 millimeters wide by 1,415 millimeters deep by 2,000 millimeters high. In imperial units, that's roughly 3.6 feet wide, 4.6 feet deep, and about 6.5 feet tall.
A sizable footprint.
But the number that absolutely staggered me was the weight. 1,145 kilograms, empty.
Just over 2,500 pounds. And that is the dry weight, before you add hundreds of pounds of liquid coolant to the internal reservoirs and manifolds.
It is the size and weight of a compact car, standing vertically next to a server rack, and that is the smaller model.
Yes.
Let's look at the big brother. Model LCS SSCR 500422K2001. This is the 500 kilowatt capacity unit we've been referencing. The maximum power consumption jumps to a staggering 55 kilowatts. The dimensions expand considerably. 2,200 millimeters wide, so exactly double the width of the smaller unit, coming in at about 7.2 feet wide. The depth is slightly more at 1,465 millimeters, and it stands 2,055 millimeters tall.
And the weight?
I genuinely had to reread the specification table to make sure it wasn't a typo. 2,300 kilograms. Empty weight.
Over 5,000 pounds.
That is the physical weight of a heavy, full-size pickup truck, like a Ford F-150, condensed into a 7-foot wide metal box. And again, that is just the cooling attachment. It doesn't include the weight of the AI server rack, it's cooling.
Which brings up an immediate, terrifying logistical reality for any facility manager.
Yeah, how do you even get it into the building? You can't just throw a 5,000-pound box onto a standard pallet jack and push it down a data center hallway.
You absolutely cannot. Raised data center floors are essentially metal grids supported by pedestals designed to allow cold air to flow underneath. They have strict point load capacity.
So they would just break.
If you roll a single 5,000-pound object over standard floor tiles, they will buckle and collapse. Furthermore, standard freight elevators in older office buildings often max out at 3,000 or 4,000 pounds. You literally couldn't get the monolithic unit to the third floor.
Which perfectly explains a very specific, crucial engineering note included at the bottom of the 500 kilowatt specification table.
Yes, I was hoping you'd catch that.
It states, note, designed with a modular architecture, each module maintains a footprint similar to the 200 kilowatt Sidecar, enabling comparable packaging dimensions and shipping weight for easier transportation and installation.
This is where the structural engineering really shines. They recognize that a single monolithic 5,000-pound block of steel and copper was logistically impossible to deploy in the exact legacy environments they're trying to retrofit.
So they designed it to be split down the middle.
Exactly. The 500 kilowatt model is structurally modular. It ships from the factory in distinct pieces that fall within the footprint and weight limitations of the smaller 200 kilowatt model.
Oh, that makes so much sense.
Facility managers can receive the shipment, load the individual modules into standard freight elevators without exceeding weight limits, roll them carefully across the raised floors, and then physically bolt them together and merge the fluid manifolds on-site right next to the server rack. It bypasses the logistical nightmare entirely.
It's like incredibly heavy, incredibly expensive industrial Lego. It makes the impossible deployment actually feasible. But going back to those power consumption numbers, 19 kilowatts for the small one and 55 kilowatts for the large one.
It forces us to confront the total power envelope of the AI revolution.
I mean, think back a decade. Wasn't 10 to 15 kilowatts the total power draw of an entire fully populated rack of enterprise servers?
It was. A standard enterprise rack might have drawn 8 kilowatts total. Now, just the fan and pump accessory bolted to the side of a modern AI rack requires 55 kilowatts of continuous power just to exist. And that is before you account for the 500 kilowatts of power required to actually run the GPUs.
It highlights the immense, almost frightening infrastructural strain this technology requires.
The source material also provides vital context by placing this sidecar within Supermicro's broader portfolio, which they call Data Center Building Block Solutions, or DCBBS.
DCBBS, right.
The document lists that this ecosystem spans GPUs, networking switches, complete racks, site infrastructure, and various cooling methodologies. It lists in-rack CDUs, massive outdoor dry coolers, in-row cooling units, rear-door heat exchangers, and of course, the L2A sidecar.
So they aren't just selling one isolated product, they're selling an entire methodology.
Exactly. They recognize that there is no monolithic legacy data center. Every building has unique architectural constraints. Some facilities might have high ceilings but weak floors. Some might have the structural capacity to install rear-door heat exchangers directly onto the racks.
Right.
Some might actually have the real estate and budget to pour concrete and install the massive outdoor dry cooler. The L2A sidecar we dissected today is just one highly specialized, incredibly powerful tool in a much larger engineering toolbox designed specifically to bridge the gap between exponential AI demands and uncompromising physical reality.
This has been an incredibly dense journey through the literal plumbing of the future. Let's synthesize what we've unpacked today. We started with the paradox of dropping a hypercar engine into a vintage chassis, and how the physical infrastructure of legacy data centers is the biggest bottleneck to AI deployment.
It really is the main hurdle.
We explored how Supermicro's L2A Sidecar CDU acts as the ultimate localized bridge, using a closed-loop liquid plumbing system to capture 500 kilowatts of heat directly from the processors.
We examined the sheer industrial brawn required to move that thermal energy, the heavy metal piping, the towering copper radiators, the N+1 redundant centrifugal pumps, and the sub-millisecond automatic transfer switches that guarantee continuous uptime to prevent catastrophic thermal runaway.
We discussed how the system leverages immense intelligence alongside that brawn, utilizing variable frequency drives to exponentially reduce power consumption, and integrating with modern IT protocols like Redfish and RESTful APIs, effectively transforming a mechanical cooler into an orchestrated, predictive node on the network.
The software really is just as impressive as the hardware.
Yeah.
And finally, we grappled with the sheer physical scale of the hardware, looking at modular machines that weigh as much as an SUV, consuming 55 kilowatts of parasitic power just to allow an older, air-cooled building to run the hottest AI workloads seamlessly.
It is a remarkable, necessary piece of transitional technology. But I want to leave you with a final thought, building purely on the thermodynamic premise established by this hardware. We have established that the L2A sidecar is a brilliant, localized bridge.
Right.
It aggressively rips the heat out of the liquid and pushes it into the ambient air of the room, forcing the building's legacy air conditioners to handle the load.
Right. It solves the rack-level thermal crisis.
But if we are now deploying arrays of 5,000-pound machines into existing buildings, purely to force the ambient air to absorb the massive concentrated heat of 500-kilowatt AI racks, how close are we getting to the absolute physical limits of the air itself?
Oh man, that is a wild thought.
The sidecar solves a localized problem, but it transfers an unbelievable thermal burden onto the room's macro environment. Eventually, will the air inside these legacy buildings, the sheer volume of oxygen and nitrogen, simply refuse to take on any more heat, no matter how fast we spin the VFD fans or how many modular sidecars we deploy?
That is a terrifying and fascinating physical limitation. When does the ambient air just break? Well, we will leave you to ponder that thermodynamic endgame. Thank you for joining us on this deep dive into the hidden heavy metal infrastructure powering the AI revolution. Every time you generate an image or query a model, remember the massive pumps spinning in the dark to make it happen. Stay curious.